Welcome everybody. Today is our first real lecture on image processing, and it's always a good idea to start at the very beginning, right? And therefore we will look into how digital images are acquired, and then we'll begin looking into how digital images are represented in the memory of our computers. And I will conclude all this with a summary, and as promised last time, I have added a couple of exercises, and you will see that today's exercises are rather trivial, but I'll come back to that later. So, where do digital images come from? How do we get them? What are images? Of course, last time we ever so briefly mentioned Photoshop or the GIMP, and there are other software packages you can use to create your own digital images. But our focus in this lecture series is rather on acquired images than it is on handmade ones. Of course, there is software you can use to create digital images, but we shall assume that we're interested in images that are recorded using cameras. Okay? And the general principle behind the idea of a digital image is actually to visualize, record, and store light. And if we agree on that, then we can ask, well, so what is light? And maybe we all remember or know that from our education early on, prior to getting to this class, that light is an electromagnetic phenomenon. It's a wave phenomenon where energy propagates in terms of waves, electromagnetic waves. And a very peculiar thing about light is that it is also a particle phenomenon, a quantum phenomenon, where photons, that is tiny elementary particles, carry that energy. Light is both, which is one of the fundamental strangeness about the universe. Light is a wave, and at the same time light is a particle. And still we know a lot about light. In particular, we know that the speed of light is a constant. We call it c. Well, it appears to be a constant. There's like very recent discussions in physics whether the speed of light changes over, I don't know, period of time periods of the sort of age of the universe. But for all intents and purposes, for us, it's a constant. It is a constant, and it doesn't matter sort of where we are. Light always has the same speed, called c, and this speed can be expressed in terms of a frequency, mu, times a wavelength, lambda. These are Greek letters, and to those of you who are not so familiar with Greek letters, well, you may know by now that they appear quite frequently in all the literature you may be reading. So this is the Greek letter nu, and this is the Greek letter lambda. In Latin letters that would be N and L, but typically these things are referred to using the Greek letters, so I will also use the Greek letters. And for those of you not so familiar with them, well, it's probably a good idea to get used to that. Right? But whenever we encounter a new Greek letter, I will inform you about it. So speed of light is frequency times wavelength. And I said it's a phenomenon where energy is being transported, and this energy is given, capital E, the energy, as a constant called h times nu. And if we plug or solve this equation for nu, we see that this energy is given as h times c, speed of light, over lambda. And this h is a very, very small number, extremely small number. It's 6.6 times 10 to the minus 34. This is called Planck's constant. Let's quickly verify if this equation makes sense. So this is H has the physical unit, joule times seconds. So here we have something joule times seconds times meter over seconds times meter. Length is measured in meters. So the meters and seconds cancel out, and yes, indeed, this is energy something in joules. So that equation makes sense. And if we look at how this speed of light is defined, we, looking at this equation, first realize that if we are talking about a high frequent light wave, we can see that it carries more energy. The larger this factor nu is, the larger is the energy, right? H is a constant. But there is this reciprocal relationship between wavelength and frequency. Here is my drawing of the electromagnetic spectrum. And according to the previous slide, we can talk about light in terms of the wavelength, lambda, and in terms of the frequency, nu, measured in hertz. And you see that for growing frequencies, the wavelength shrinks. Picture this. You have, I don't know, some unit interval. Let's call this distance 1. Right? And then there is a wave like this, like so, wavelength 1. And if you have like lots of peaks and valleys in this interval, then you have a higher frequency. Right? Lots of peaks and valleys is the wavelength shrinks, but the frequency increases. We can see this in this diagram. And you can also see that there is a fairly large spectrum, right? This goes from a frequency of 10 to the 8th up to 10 to the 18th, or in terms of wavelengths, we're talking about something that can be of the length of a meter up to something 10 to the minus 9, for example. These are really large numbers, and this is a really, really small number. So this electromagnetic spectrum covers a really large bandwidth of frequencies and wavelength. And very, very interestingly, the part of the electromagnetic spectrum that we can see, that our eyes can perceive, is just a very tiny fraction. And I have exaggerated that here. This is much, much narrower, much narrower. The take-home message is that what we see, what our eyes can perceive, what the human body is able to make out of light that is incident to our eyes, is constrained to this really narrow band here. And there are many, many, many or large portions of this electromagnetic spectrum of larger wavelength or smaller wavelength or lower frequency or higher frequency. And everything sort of that is to the left of the visual spectrum, which sort of has smaller frequencies than red light, is called infrared. Infra is a Latin for sort of lower or below of. And everything that has a higher frequency than violet light is called ultraviolet, where ultra is again a Latin prefix indicating higher than or beyond of. And so we have the visual spectrum, we have what is called infrared light, we have what's called ultraviolet light, and there is a lot of infrared and ultraviolet light around us, but we just don't see it. Because our eyes, the human visual system, is only able to perceive this tiny part of the electromagnetic spectrum. A very high frequency light is called X-ray radiation, and very low frequent light, this is all light, but we just see a part of it, is called microwaves. And now that we have seen that, that there is, well, you know, really ever so briefly saw, that there is something called electromagnetic radiation, and that just a tiny fraction of this whole spectrum of electromagnetic radiation is visible to our human eyes. We can then ask, okay, so how do we record this electromagnetic radiation? How do we visualize it? How do we make it visible? How do we record and store it? There are basically three major principles or sources for technology that records light. First one is reflected light. And then we have absorbed light and emitted light. And things we can see because they reflect light. What our eyes perceive of the world that surrounds us is light that, in our case, say, comes from these many tiny lamps and probably from the sun outside, hits this chair, is being reflected, hits my eye, and so I can see the chair. Interestingly, the chair is very dark, so basically it hardly reflects any light. It's black, but this is really bright, so there is a lot of light being reflected from this part of the environment I am in into my eyes. And if we are talking about photography, in the sense we are familiar with it, then we can now realize that a digital camera, or a camera in principle, that records the kind of light we can see, basically emulates what our eyes do, and that is to say that cameras, in the sense we are used to, record reflected light. And we know that from photography or from scanners where we scan documents. Those are all technologies that record reflected light. But then there are technologies that record and then visualize absorbed light. And the canonical example is X-ray images. If you have a medical exam and they take an X-ray of you, what they do is they expose you to extremely high frequent light, something around here, and that light is so frequent, so full of energy that it basically goes through your flesh. But it does not go through your bones. The density of your bones is higher than the density of your flesh. And so the bones will block out or absorb that light they expose you to. And the light that sort of goes through you, because it's not absorbed by your bones or whatever, hits this recording device. And so therefore, when we look at X-ray images, what we basically visualize here is not reflected light, but absorbed light. The fact that we can see the bones is sort of, in a sense, this is a negative image. This is an image that has recorded what has been absorbed. And then there's also technology for recording emitted light. And emitted light, usually in the context we record it, is heat. We all have a certain body temperature, and we are all radiating bodies. This is, in a very abstract sense, we are sort of all not really radioactive, but our bodies, just as radioactive material, constantly radiate energy, and that energy is heat. It's actually carried in forms of light, and we can visualize that. We can record active sources of light, and these are the infrared images in this example. They take an infrared image. We see that here, this human hand, there are certain areas that are hotter than others. Interestingly enough, it's the fingertips that are very hot. This is because there's lots of nerves there, and sort of like they need lots of energy, lots of blood is flowing through those. There is heat coming from our fingertips. And it's not so recently, I have to be careful. have to adapt this lecture every couple of years. But rather recently, this idea of recording emitted light has been taken to the next step, because nowadays we have these kind of devices. This is the Microsoft Kinect, right? I don't know, costs 100 euros, has become extremely cheap. Those are cameras, and here we can see sort of a professional earlier version of these kind of cameras. You can still buy them, I guess. And what we see here is an array of infrared diodes which emit light. We don't see it because it's infrared. Our eyes cannot see this. But these tiny things here, they emit light. And that light is being reflected. And that actively emitted light is then recorded by these cameras. Here is the camera, here are the emitters. They emit light, that light is being reflected and is then recorded. And this is exactly the same principle that is being used in radar technology, where something is emitted, is reflected back, and what is being measured is the time it takes for something that was emitted to come back. And because these times can be measured, we can indeed actually measure the distance of something that has reflected these kinds of light waves. Right? Because we know that speed of light is a constant. If we know the frequency with which we emit light, we can sort of do the math and solve that for distance. And then there is another kind of technology that is becoming more and more important, basically because it is becoming more and more cheaper. This is the idea of hyperspectral imaging. It actually works exactly like conventional photography. These kind of cameras, hyperspectral cameras, record reflected light, but they record reflected light on a larger part of the electromagnetic spectrum. They record many wavelengths at the same time. And I have illustrated that here. This is a satellite image of, I don't know which region of the world it is, that has been recorded using hyperspectral signals. So here at the top of the stack, we basically see a usual photographic image. But this image here is actually a stack of many images. And each of these images has recorded a different aspect of light. And we'll talk about pixels soon, but the pixels in these kind of images look like that. They are curves. Every pixel is like an element of this image is actually a tiny stack of pixels starting here, going all the way to the final layer. And if we plot like these individual pixels, we see something like that. It's very interesting because using this technology we can see inside things, because these are able to record responses of higher energy, stuff that sort of is going, say, inside your skin and then it's being reflected at your bones or whatever. Okay, so there are different ideas as to how we can visualize electromagnetic radiation, light, and how can we now record it? So this, all the examples I've shown you, of course, already shown you that it is possible to record it, but how do we do that? And basically, at this day and age, the way we record images, the way of how to do imaging is based on this idea of CCD cameras. And this abbreviation CCD is a shorthand for charged coupled device, which is to say this refers to a semiconductor device, an electronic part that is actually composed of a lot, like thousands of photosensitive elements. Yeah, I have to adapt these things. If you go out trying or wanting to buy a new camera, you will, I don't know, have a hard time finding a camera out on the market that has less than 3 megapixels, which is to say that for modern cameras at least you will have 2592 times 1944 photosensitive elements on these chips. Here is how that looks like. So if you were to open your camera, remove everything, I don't know, say the lens and stuff, you eventually see this here. This is a silicon thing, microchip, and that consists of lots of tiny things like this. This is really just a schematic. Right? There are like thousands in this direction and thousands in this direction. How does that work? So I've already said that light is something that carries energy, or it's like composed of tiny particles called photons, depending on our point of view. And what we see is actually reflected waves or reflected photons, as you wish. So basically, if you point your camera at something and take a picture or a video, what happens is that wherever you point your camera at will reflect light, and this light will then sort of hit the lens of your camera. And from the lens, it is being sort of focused onto this chip, onto this array of photosensitive material. And depending on the energy or number of photons that hit one of these tiny things, we can sort of compute that into information that represents what we see. Was that all? Oh yeah. So light is being reflected from stuff. It hits the lens of the camera lens focuses it on this chip, and these tiny elements on this CCD chip sort of record the energy or amount of photons in terms of numbers, which we then of course can represent in a computer. How do we record color images? Right, of course we see different kinds of colors, and it would be nice if a camera could do the same. There's different ways of doing that. One idea is to split the light that hits the lens into different channels or frequency bands. And typically what is considered there is red, green and blue. Right? So behind the lens there is, in certain cameras, an apparatus called a trichroic prism, which if sort of rays of light hit this prism, physics allows it to, you know, be broken into elementary frequencies or wavelength. And so therefore a ray of light that hits this prism is split into 3 parts, and these 3 parts can then be recorded separately. One for the red component, one for the green component, and one for the blue component. This gives digital pictures of very high quality, but still is a very expensive idea. Because like, these things are expensive, and you would have to have 3 different chips. So that is expensive, but is being done, and for high quality photography this is what they do. There is a cheaper alternative, and it's really cheap. Here we just have one CCD array, one CCD chip consisting of these photosensitive elements, and superimposed on top of that is a layer of extremely tiny glass shards. Right? And they are colored, you know, actually not in blue, green and red, but I do it for visualization. So basically this is to be read as these are color filters, and this pixel here only records blue light, or that is light in a wavelength/frequency that we would call blue. And this pixel here would only record green light, that is light, the wavelength / frequency would call green, and for red as well. This is a bit crazy because we can already see that if these things are used to capture images, to record pictures, we end up with a representation of the scene that has been recorded, where the different pixels sort of carry different color information. It does not really matter, we don't see this because these pixels have become so small that our eyes cannot resolve these issues. And we can also use interpolation to sort of interpolate the blue information from here to this pixel and so on and so forth. And these are things we will look into later on. This is typically what is being done in your, say, cell phone cameras, consumer cameras. This is not really high quality photography, but it is indeed much, much cheaper than the idea of using trichroic prisms. Okay, some more details. How do these CCD elements work? Light is incident to the lens of your camera. The lens focuses it onto this area of charged coupled devices. And whenever a single photon hits one of these microconductor elements, it generates a charge. That is, an electron is freed. The more photons hit such little element, the more electrons are freed. Right? And we have to remember that we are talking about quantum effects here. So like there is extremely many photons in very, very tiny fractions of a second. So it's not just one electron that is being freed, but thousands. Basically, this technology turns light into charges. And well, these charges can be stored using elementary electronic devices again. And once they sort of have been stored in terms of charges now, it's not light anymore, but it is really electromagnetic charges, we can read them off these tiny photosensitive devices and store them in the memory of our computers. And again, depending on the quality of whatever camera you're using, these tiny elements are able to record between 100,000 and sort of 350,000. Like these numbers, I don't know if they are still technology progresses, but they can, you know, store a lot of, I shouldn't say that electrons, but they can deal with sort of range of charges here. And if there is more light incident to one of these photosensitive elements, it will saturate. And you know that if you point your camera into a light source directly, the picture you will get is extremely bright. And that is basically you have overburdened your camera. Yeah, now, say we are dealing with a low-cost camera. It could, in quotation marks, record 100,000 electrons per CCD element. And then we would want to store this. I'd say we can indeed determine the number of electrons that have been stored with this precision. So it's either something zero, there cannot be a negative number of electrons, right? I mean, that sort of light is being extracted out of your camera, but this thing records light that is incident to your camera, and there is either light or there is not. If there is no light, then there will be 0 electrons be freed. If there is a lot of light, then there will be 100,000 electrons be freed. So no light, 0 electrons, lots of light, lots of electrons. We would want to represent the fact that we can have between 0 and 100,000 numbers per CCD element. We would have to have a storage capacity of 17-bit per CCD element. And that is not feasible as of today. It is too memory intensive. We would have to have a huge memory chips in our cameras. We would have to have the capacity of actually really being able to determine the amount of energy with precision like that. Still not feasible. Too memory intensive, technically not really feasible. And the good news is it's not necessary. It's not necessary because even though we are very proud about our eyes, they are not good enough. They wouldn't recognize that anyway. So even if you were to record an extremely high quality image, that would be in vain. No human observer could tell the difference between an extremely high quality image and an image that's of like slightly less quality. It's not distinguishable for us. And we will talk about this towards the end of this semester. Towards the end of this semester, we'll come back to how the human visual system does it, and then we understand that indeed, yeah, this would be overkill. So what is being done indeed? Instead of recording the fact that, let's I have to be careful and exaggerate this, there is like 3 electrons being freed by the amount of light incident to a certain element, CCD element, or 5 electrons being freed, and this is not being distinguished. This is basically to say, this is a simple schematic representation of what's going on. I could, but then again couldn't distinguish that. Draw, I don't know, a stack from 1 up to 100,000. So I sort of confine myself to 15 here. But we see we have either something very dark, that is a lower amount of electrons being recorded here, or something very bright, that is a larger amount of electrons being recorded. And instead of, looking for these numbers, what cameras do, digital cameras do, is they sort of say everything that is, say, between 1 and 3 electrons, that you have to multiply this with large numbers, say 10,000 or whatever, is represented as color value 1. And everything between 4 and 6 electrons is represented as color value 2, and so on and so forth. This is called quantization. What's happening here is that the whole sort of spectrum of charges that could be recorded is quantized into bins, where the lowest bin here represents a certain range of possibly recorded charges. The good thing is that this can be done very quickly, technically. This is nothing that needs to be sort of computed every time you take an image, but this can be realized on the hardware of your camera, and so therefore indeed we can do this really quickly. No problem there. We'll come back to this later. It's a sort of difficult mathematical operation, but technically this is realized in terms of such lookup tables, say. So the camera does not have to compute something, it just pipes something through an architecture, and this comes out automatically. And in this schematic representation, I have sort of squeezed 15 bits into 5. Typically, in your cameras, this would be 8 bits. And we know that 8 bits represent 1 byte, and that is to say, if we are talking about photography, at least consumer market cameras, what they still do to this day is that per photoelectric element of your CCD chip, they have 1 byte of memory. And that basically says that the quantization that is being applied is sort of determined by the memory of your camera. And 1 byte of memory per photosensitive element is, of course, 8-bit, is to say that we can represent 256 different intensity levels per tiny photosensitive element. So 8 bits per element. High quality cameras or high quality scanners exceed that, they go to up to 14. I don't know, maybe today they're already at 16. I don't know. This technology progresses, and it is very tedious to update these slides every so often. Here's a thing I have to mention when we're talking about how digital images are being recorded using cameras, or how images are recorded using digital cameras. These photosensitive chips, they are slightly distorted. Look at this. I did this on purpose. These are not perfectly square. These are tiny rectangles, and this is indeed what's going on these chips. And so therefore, the images we record using these technologies might be a bit stretched in one or the other direction. That depends. Again, this is not a problem if we know as to how much such a tiny element is distorted. We can, record the light and then sort of apply mathematics, which we will learn about later on, to correct that. So if we look at a digital image, we typically do not see any distortion. That is because what is recorded has been corrected automatically. Here is another problem with this CCD technology. I said that these tiny devices can store up to a certain amount of electron, up to a certain amount of charge. And if that is being exceeded, we can observe something that is called blooming. Can everybody see this line here? Yeah? Do you see it? Is the beamer good enough? Okay, so what happened in this image is there was something really bright here, maybe a lamp, I don't know. The camera was pointed to that part of the scene, the picture was taken, and here there was so much charge being freed on this CCD device that individual elements couldn't handle that anymore, and that caused these charges to spread from here to there, to there, to there, to there, to there. So they sort of infect their neighbors. These charges overflow and spread to these neighbors, and this is how we get these lens flares. Lens flare is something else, but this is how we get these crazy lines that look like tiny stars. This is called blooming. Overcharged elements or electrons from these overcharged elements may overflow to the neighbors. And here is something else. We don't see anything here, right? I can see something on the screen, or can you see that it is slightly brighter here than there? Is that visible? Okay. Basically, this is a picture taken in the dark, but there must have been something that was radiating heat. Our eyes wouldn't see that because our eyes just perceive what we call the visual spectrum, right? This visual, the part of the electromagnetic spectrum that is visible to us. But these CCD sensors, they can record infrared and ultraviolet, right? Tiny parts. Not all of that, but they are not sort of perfectly constrained to what we see. They can see below and above that as well. See below and above that as well. Maybe you test that at home. An experiment you could do is in your kitchen, you boil a pot of water and then turn off the light, make it really dark. Take your camera and take a picture of the pot of water that's boiling. Maybe you'll see something. Right? And this is called dark noise. That is to say, even if you record a picture where you shouldn't see anything, you may see something. That is because this technology is not a perfect emulation of the human visual system, and I guess it's not even meant to be a perfect emulation of the human visual system. Okay, now we know there's different ideas as to how we can record light: reflected light, absorbed light, emitted light, right, at different wavelength. We know how it is done. This is basically translating light waves or photons into charges, electrons, which we can sort of record. Now we have them, and the question is how to proceed from there. You said, okay, in memory there is typically 1 byte per pixel, as these things are called. How do we proceed storing these images on hard drives, memory chips, whatever? Once we're talking about this, actually we are not going to talk about this, but if we were to, we would have to look into the idea of different file formats. And you all know that if you have a fancy camera, it typically allows you to store the images you record, the pictures you take, in the so-called RAW format. And that is indeed, whatever you record, whatever picture you take, is being stored 1 byte per pixel and per color channel. And this gives you very large files on your memory chips. You may also store them, say, in JPEG, GIF, PNG, TIFF, whatever. There's like a whole zoo of these things. And all of these are basically fancy ways of compressing this, of trying to throw away unnecessary information contained in here, but keeping the important ones so that if it is stored, say, in terms of a JPEG compressed image, that after uncompression it still looks reasonable to the human observer. We may talk about this, but compression is not our main focus in this lecture. And here's a table that is funny to me, probably not to you, because what did you do in 2003? I don't know, 10 years ago. So what I did in 2003 is I taught this lecture for the first time, all right? And back then, it's like, you see, I have to update these slides. So back then, in 2003, the typical consumer market camera had a resolution of 3 megapixels. Right? And we now know what that means, basically the number of photosensitive elements in X and Y direction. Then in 2009, that was 12 megapixels, and last time I taught this, it was 17, and then I stopped counting. This is ridiculous. Because you see what happens. Back in 2003, so it's like 11 years ago, there was like, seriously, if you had a cell phone, and nowadays they're called smartphones, right? But if you had a cell phone, so it's a Nokia thing, there was no camera in there, all right? There was no, it might be hard to believe, but indeed there was a time where there were cell phones without cameras. 5 years ago, that was a commodity device, right? And nowadays, you can't even buy a phone without a camera anymore. I don't know, I mean, you might, but yeah. Back then, in 2003, so what would you have to spend for these USB chips on which you record your pictures? Right? Back then, for 100 euros, you could get 100 gigabytes, and there was a factor of 10 in these 3 years. It went from 100 gigabytes to a terabyte. And in 2012, it was 2 terabytes. I don't know where we are right now. I basically stopped extending this table because of this, right? Indeed, it might be hard to believe, but there was a time where Facebook did not exist. Okay? Facebook was started in 2004/5 and became really popular in 7/8. And in 2009, it was already a site on the web which had 10 billion pictures stored, right? That was as of November 2008. I don't know this number. Let's go for Flickr. Flickr, do you know Flickr? It's a photo sharing site. Hard to imagine photo sharing sites did not exist in 2003. Seriously, believe me, did not exist. In 2009, at least as of November 2008, there were 3 billion pictures available on Flickr. And in 2012, it was 6 billion pictures. And for Facebook, we are talking 10 billion pictures in November 2008. And nowadays, even 2 years ago, it was already the largest, and by far, the largest repository of digital pictures on the planet. There is no other company, no other service Back in the day, you know, there was these press agencies that had huge image databases, which you could have bought, I don't know, and then search these databases for images you might want to use for illustrating something, blah blah. This is all water down the bridge, right? 10 billion pictures, that is more than you can buy anywhere, and nowadays this is at least grown at least by another factor of 10. So at least 100 billion pictures on Facebook. And it really became too tedious for me to continue this table, to update it. It's just for you to see that, you know, these things progress incredibly quickly. So it's fun. But I will not contain updating this table, and so it will be ever more fun every time I give this lecture. Okay, we have now looked into the technological underpinnings of digital imaging, and it is now time to approach the question as to what to do with the images that are being recorded. And that is to say that we now have to approach the question how to represent them, or how to think of images. What could be our mental picture of a digital picture? What could be our way of thinking about these things? Now, the first thing we have to always keep in mind is that because of the technology we ever so briefly sort of skipped through here, digital images are digitized and quantized. And that is to say, the domain and the range of a digital image are discrete. And by domain, I mean the spatial resolution, right? That is sort of the width and the height of your image. That is basically the number of pixels in X and Y direction. And this is not a continuum. With chemical photography, you know, back in the days, there were like these films you had to put into a camera. Back then that was continuous, but with digital images this is discrete, because these CCD chips consist of a large but fixed number of distinguishable tiny elements. So the resolution of the picture consists of lots of tiny pixels. And it's not continuous, but it's discrete. And we already talked about the fact that we do not store between 0 and like some large number of electrons, but we store them in packages. Right? We quantize the amount of charge that is being recorded by these elements. And that is to say a digital image is quantized. And that is to say the domain, resolution, right, is something discrete. But also the values we can store at each point are discrete. And I have said it so many times already, because why shouldn't I? The smallest basic element of a digital image is called a pixel. And pixel is a short form for picture element. And therefore, here is the first picture we can think about when we think about digital images. A digital image consists of a matrix of pixels. And here is such a matrix. So first thing you may notice is that I have moved the pixels together. So this like tiny gaps we saw a couple of slides ago is gone. Let me go back to the tiny gaps. These tiny gaps here, these, technically they are there. We abstract them away. When we are talking about images, there are no gaps until in a couple of weeks from now. No gaps. We think of an image as something like that. This is a two-dimensional array. It has two dimensions, consisting of lots of tiny things we call pixels. And we may address these pixels using their x and y coordinate, or I and j coordinate. row and column coordinate, whatever you have. I will, from now on, switch quite frequently. And that is not because of malintent on my part, it's just because depending on what I'm talking about, it might be better to talk about X and Y, row and column, I and J. Be warned. Right, so if I'm talking about I and J and then 5 minutes later about X and Y, don't be alarmed, just be aware of the fact that I may talk about whatever suits me. So we can address these things like this pixel here. Let's call it Pij, would be the pixel in row I, column J. Right? This is how we can address them, nothing special there. If we are talking about color images, we already ever so briefly mentioned the idea that color images are recorded in terms of 3 such pix maps, 3 such arrays, 3 such matrices, one for the red, green, and blue channel. And depending on how fancy your camera or your software is, there's maybe even a 4th channel, which is called the alpha layer. I'm not going to talk about this right now. And the resolution, well, we already talked about megapixels and so on and so forth of digital images, can therefore then be characterized in terms of the width and height of these pix maps. Right? And typically these pix maps consist of pixel arrays with a ratio of 4 to 3. And it's like there's typically more pixels along the X direction than along the Y direction. And the ratio is typically 4 to 3. And I should probably update this. Yeah, this is 2 numbers of number of pixels in the X direction, number of pixels in the Y direction. And back in the day, 1024 times 768 was fairly okay resolution. We have to multiply these things by, I don't know, 4 by now. Yeah, but here you see, this is the number of elements along the X direction. This is the number of elements along the Y direction. This is in a ratio of 4 to 3. If we have width, height, and color depth of an image, we can now then compute the amount of memory or storage requirements we have to plan for if we want to store such an image. For this example, for instance, say it's a color image. That is, we have 3 color channels. For every color channel, we record 1 byte. So this image, if it's a color image, would require memory of the order of 1024 times 768 times 3 bytes, and that is about 2.3 megabytes. This is funny because nowadays this would be considered a really low resolution image. But already, if we don't think about compression, it would eat up 2.3 megabytes of memory in your computer. And that is no problem at all. Like even your smartphone would not suffer from that fact, because like I should, in this table also had a column for how much memory a smartphone has. These numbers grow. But the take-home message here is that even fairly low resolution images can lead to surprisingly large amounts of memory required to store them. And again, this is if we store these images in non-compressed format. So ever so, like really, really briefly, let's go back to these image formats. Image formats are protocols, basically, recipes somebody has agreed on, for how to store images on, I don't know, the memory chip of your camera, on the hard drive of your computer, on some server at somewhere, Facebook, whatever, or on DVDs. There's nothing else, but like a DVD stores, lots of images. And there's a great variety. We already saw that: JPEG, GIF, PNG, TGA, TIFF, and so on and so forth. And the ones I show you here, they are also called pixmap formats, or raster graphics, or bitmaps. And this is because they all start with the idea that a digital image is such a pix map, such a matrix of pixels. And there are other formats, such as SVG, with some S, I don't know, vector graphics, and FIG is figure, I don't know what the S is for. Anyway, these are file formats for digital images that do not represent the image as a pix map, but rather as a collection of lines, circles, and so on and so forth. Right? These are the things we are not at all going to talk about in this lecture if you use, I don't know, Inkscape or programs for drawing graphical graphical pictures. You typically store that in these formats. And what you typically do is you draw rectangles, circles, whatever, polygons, stuff like that. And if they are being visualized on your monitor or on your screen, then of course they are visualized in terms of a pix map, because that corresponds to the way monitors work. But if you create them and if you store them, what the computer does is say, here's a line that starts here and ends there. And it's not like a collection of pixels that are black, but it's a line that starts here and ends there. Or it's a circle with a center here and a certain radius. So these things are stored in these formats, and all of these formats are basically, this is lots of pixels. Lots of pixels. Yeah, we are not, yeah, maybe, I don't know. That depends on how fast we can progress with the lecture. Typically, I'll not go to talk about how images are being compressed. This is a science on its own. But we may note that compression, or these formats other than RAW, JPEG, GIF, and so on and so forth, are used to reduce the amount of memory that is required to store a digital picture. And whenever we do data compression, this is something you have to keep in mind, we annihilate information. So compression is the science of trying to throw away only that kind of information that's not really useful. And in our scenario here, that is to say, only throw away that information that does not assist the human visual system in one way or another. And I have to stress that because if you, I don't know, my favorite example is there is a science fiction film called Blade Runner. Do you know that? Blade Runner. In Blade Runner, this is from the late 80s, it's a great movie, it's slightly dated here, but there is a famous scene where a cop is checking the security footage of a surveillance camera. And he's zooming in, zooming in, zooming in, zooming in, zooming in, zooming in until sort of the micro level. Well, either that camera has recorded everything on the micro level, or that wouldn't work. Right? And you can make that experiment, of course, with the pictures you take. Like you take a picture with your phone, and then you watch it, and then you zoom in and zoom in and zoom in, and eventually you will start seeing the pixels, because all of a sudden it becomes blocky. But you will not start seeing more and more and more and more details. We can do, interestingly, we can do this nowadays. This is called hyper-resolution images, where instead of taking a picture with just one camera, you have, say, 10 by 10 cameras. You take one picture, all of them at the same time. And now you have 100 pictures. And these 100 pictures, using the marvels of mathematics, can be computed into something so that you can zoom in forever. But if you have just one CCD chip, you cannot. And in particular, if you have taken a raw image and then you use some compression software to store it as a JPEG image or as a GIF image, once it has been turned into a JPEG image, you can never ever get the original image back out of that. I have to stress that. If we apply compression, we remove information, and once that is gone, there is no way of getting it back. So the science in this area of compression consists in finding ways of throwing away information such that the difference between the compressed image and then uncompressed image and the original image are not really visible to the user. And I said details maybe later because in order to understand what, say, JPEG does or MPEG, we first have to really dig deep into stuff we're doing anyway, and then if there's time we can look into it. And what do I mean by differences are hardly visible to the eye, but they are there? To see that, let's single out one of these digital image formats explicitly. And this one is the example we're talking about here is called is about PPM images, and PPM is shorthand for portable pixel map. And here I have used a hex monitor to look into a PPM file. If I will use an image viewer, I wouldn't see this, but a picture, actually what I would see is this. So this is the, and we see the pixels for this because I have made it large. This is the image that if we look at how it is stored on disk in terms of a PPM file, it would look like this. There's a couple of lines we can read, which our brain can make sense of. The first line contains the so-called magic number, P6 in this case, which tells us that whatever is to follow here is sort of binary information, binary way of storing data. Could be stored otherwise, then it would be like P1, P2, P3, whatever. Then the next line is a comment, and it tells us that this image was stored using a program called XD. The next line contains two numbers, and this is basically the resolution, so it's like 74 times 82 pixels. And yeah, so it's 74 times 82 pixels. You see the pixels because if I would not have enlarged it, it would be a tiny, tiny speck here, but I have made it larger so that we can see that. And the next number indicates the color depth, which is 255, which is a byte. So we just looking at this, we know, okay, this here will be binary information, and it will represent the color image. This is according to this P6 here as well, and the resolution is 74 times 82 pixels, and the maximum color depth per channel is 255. So there will be 3 bytes per pixel now. And yeah, that's what happens here. This is the image. And there is 1, 2, 3 bytes per pixel, 1, 2, 3 bytes per pixel, 1, 2, 3 bytes per pixel. FF is what number? 255. And earlier on we said that bright stuff is represented in terms of larger or smaller numbers? Larger numbers, okay. So we have red, green, and blue, and we have 3 large numbers. And what color could that be? White. Let's see. Oh yeah, it's all white here. It works, right? Let's see if there is some. No, wait, wrong direction. Yeah, eventually, so this is basically to say this is line by line by line, and the first couple of pixels in this first line are white, 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 and then eventually there are other colors. This is how this PPM image is stored on this in terms of RGB triplets, and where these triplets are represented in terms of hex numbers. Here is the image, and yeah, this is another hex dump of this. This is basically an extended version of what we just went through. Here we again see this is how the file begins, and here is the image. Now, once again, the image looks like this. If I would have stored the image as a JPEG file, it would look like this. So this is why only one picture here, it doesn't make a difference. But if we look into the JPEG file, it looks different. And this is because it's a different file format. So we have a different header here, and not only the header is different, but also sort of the information that represents the image. What I'm trying to get across here is that the two files look different, but if I really would visualize the PPM image here and the JPEG, there would be no difference. There would be no difference. At least not perceivable to us. And yet it is there, because if we look at the corresponding file sizes, we see that the JPEG image is 10 kilobyte, whereas the PPM image is about 18 kilobyte. And this is funny, it's such a tiny image when we're talking about kilobytes here. Okay, that's all I've got for today. We are now prepared to dig deeper. Right? We now know about different ways of visualizing light. We know it can be, we can record reflected light, emitted light, absorbed light, can record light of different wavelength. We have ever so briefly seen how this happens in terms of physical technology. It's all based on semiconductors and on the fact that if energy hits a, I don't know, certain silicon element, electrons are being freed, and these charges can be stored. And ever so briefly, we talked about image formats. We don't really know about them, but we at least know that they are there. And this is, for our intents and purpose, basically important to know that they exist, because it already hints at the fact that we can do things with images. And if it's just that we can apply different compression modes. And we will look into what we can do with images in quite some detail throughout this lecture. And for those of you who want to do weekly exercises in addition to these projects, here are the exercises for this lecture. This is not really rocket science. But I'm just saying that it might be worthwhile thinking about this anyway, because one of these questions typically appears at the exam. Alright, that's all I've got for today. Are there any questions? No? Then we see each other again on Monday. Thank you.